All right, let's continue to part 2. Let me share my screen. All right. Okay, in this part, we're going to talk about Bayesian growth mixture models. We're going to learn why do we use mixture models in general, and how do we interpret the mixtures? Why do we use growth mixture models? Growth mixture is just a type of mixture models. How do we estimate growth mixture models in Bayesian framework? And how do we select the best fit model? And also we'll cover potential issues in Bayesian growth mixture modeling. First, why do we use mixture models? That is because mixture model is useful to investigate differences between unobserved groups or clusters in a population. So if you assume that the population is included more than just one subgroups, then a mixture model would be something you want to consider. And also the subgroups are unobserved. And those unobserved groups in a mixture model are called latent classes. So there are two different objectives of a mixture model. The first is to assign subject to a given group, and the second to estimate structural differences between the unobserved groups. So basically we assume that different group, there are potential differences across subjects and they belong to different unobserved groups, and there are differences across those groups. And we assign subjects into those groups. An example could be the measure of height. Here's probably histograms of height in a certain population. And instead of seeing the bell-shaped normal curve, we actually see the histogram like this. It seems like have a bimodal. And in fact, if we know the composition of the population, we know that half of the females and half of the population are males, and the females' average height is 164 centimeters, and average height of males in that population is 184 centimeters. And also with that distribution with those distributions mixed together, we have a mixture of distributions. So this black curve are the density curves for the mixture distribution, and then we see that the mixture density curve fit the data very well. If you argue that, well, you know the group identity, there are females and males, and then you can just use a multi-group analysis. So then that in the next example, then it's probably a better example for mixture modeling. Okay, so this example, I actually call it a Tongtong's Leaf project. It's a summer project for my daughter 2 years ago, because of COVID, she can't really do much during the summer. And at that time, she was in kindergarten. She just learned marrying stuff. So I just found her a project to kill time. And basically, I asked her to measure leaves of a tree. And this is a little cute tree she found. And she basically measured 100 leaves, the length of the leaves. And I asked her to write the length of the leaves in centimeters, and then type those into computers, and then try to categorize those leaf lengths, and then just to see the range of the length of leaves. So my expectation is that she can find out, oh, most of the leaves have a length in the middle, and the fewer leaves have are shorter, and fewer leaves are longer. So I hope she could find a bell-shaped curve and at least to get some idea of stats. Okay, but eventually she got her data. This is really the real data collected from her, and this is the histogram of the leaves length, and she measured, it doesn't look like a bell-shaped curve. It seems a bimodal, right? So if you actually put them into two categories, it seems like there are these two categories. Okay. And in fact, if you see those leaves, if you see those little trees here, actually on the very top of each branch, the leaf length, those are some baby leaves. They are all very small. But right after that, once it grow out of that stage and becomes more like a adult leaf, and then they are more of the other category. Okay, so in that case, it actually makes sense to have those two categories and actually fit a mixture model with two latent classes to her data. And here's the result. So you can see that if I just fit a one normal distribution curve, then the mean of the estimated, well, actually the sample mean is 11.18 and the variance is 16.58, but the curve of the one normal distribution really doesn't fit the data, right? Instead, for the mixture model, based on the, well, this is actually from the Bayesian analysis, okay? So based on the analysis, we have two categories specified. And for the first class, there are 77% of the leaves with the average length of leaves to be in 12.90, and the variance is 6.52. So that's probably this big group here, which takes like 77%. And the second class takes a 23% of the leaves with mean length to be 5 centimeters, okay? And the variance is 4.02. So those are the more like the baby leaves. In general, the distribution of the leaf length is actually a mixture of those baby leaves and those more like adult leaves. So we have this bimodal distribution. And I think this is a really great example of when we can use a mixture model, because by just looking at those leaves, you can't really say which leaves belongs to which category, because there are also some of the lengths like in the middle, but it's just more likely those leaves are in the baby leaves and those leaves are more like the adult leaves. So they are two unobserved latent classes. Okay, in practice, in psychology, there are more examples that can be used with mixture modeling. For example, when we study cognitive abilities, the population may include some low ability group and high ability group, and then mixed together. So if we use mixture models, it can better help us to figure out what's the group differences and which person belongs to which groups. Okay. And also when we study the response time in psychology, some people actually focus more on the speed of the response and some people focus more on the accuracy of the response. With different focuses or different goals, they actually show different patterns of the response time, and a mixture model could be a great application to analyze the response time. And usually because it's skilled and the skillness may caused by how they respond to the items. And in many other examples are available in psychology and other social sciences. After we fit a mixture model, we need to interpret those. The data in K-groups are represented in one population, so the mixtures can be used in this context to analyze differences among the groups. And there are two interpretations for mixtures. One is the direct interpretation, where the mixture components correspond to clusters in the population that have a conceptual meaning. The other is an indirect interpretation. Okay, so for the direct interpretation, it basically means that each latent class have a conceptual meaning. Like for the height of the population example, we know that one group is more likely to be females, the other groups is more likely to be males. So we can tell like this group or these latent classes are different, we can interpret the meaning of them. And even in the TOMOS LEAF project, we have also 2 latent classes. And we can actually find a conceptual meaning for each of the group, because we see that, oh, one class just include most of the baby leaves, the other class include most of the adult leaves. Okay. And for indirect interpretations, in that case, mixture components do not correspond to existing groups in the population, but they only serve to account for the shape of the distribution. For example, some of the shape of the distribution is really skewed, or they are over dispersion. So in that case, mixture model can really help us to find to fit the best shape of the data, and that can be also used as a robust technique. When we specify a mixture model, the simplest case is we can just find a mixture of a few normal distributions. So this model is specification or a model estimation. I start with this mixture model with just a few a finite mixture of normal distributions. Okay, then the likelihood or the density of the data xi conditional on the model parameters is a weighted average of the density for each normal distributions. Okay, so here this probability P of X conditional on lambda, mu, and phi. This lambda is class probability, where proportions of subjects belongs to different classes, and mu correspond is the mean of each class, and phi is the variance of each class, and it's basically just a weighted average of the normal densities. Okay, with such a normal likely function, and then for the frequentist method, basically they can use EM algorithms to estimate this model. And the Bayesian framework, Gibbs sampling, or other types of MCMC procedures can be used with data augmentation to estimate the model. Okay, for model estimation, we have in the Bayesian framework, we have to specify priors, and we need to specify priors for each of the parameters. In such a simple model, here are the priors for them. Like I already said, this mu j represent the mean for the jth component, phi j represent the variance for the jth component, and lambda j is the class probability or class proportion for the jth component. If there are 2 latent classes, then we have this mu1, phi1 for class 1, mu2, phi2 and for class 2, and we also need to figure out the probabilities or proportions for class 1 and class 2. What I want to point out here is this model can be easily generalized to other models. For example, if we have, instead of having normal distributions, we have a mixture of regressions. In that case, we're not really have mu j here. Instead of having the mean for each latent class, we're having this regression intercept and the slopes as a parameter for each class. So we have this intercept and slopes for class 1 and the residual variance for class 1, intercept and slope for class 2, and residual variance for class 2, and also the class proportions. Okay. And even for more complex models, this can just be generalized to that. Okay. And then for this, just a mixture of normal distributions, we have these parameters, and then for each of them, we can specify priors for them. Basically, for the means, we use a normal distribution with a large variance. And for the variances, we can use the inverse gamma distributions. Basically, these are more like a flat distributions, so they are non-informative. And for lambda, which is a class probabilities, we use a Dirichlet distribution. Basically, the Dirichlet distribution is a multivariate generalization of the beta distribution. remember that we talk about beta distribution when I said when the outcome variables are proportions, we can use beta distribution to model the outcome variable. So beta distribution is used to model proportions or percentage. And Dirichlet distribution, just a generalization of it. So the outcome of the Dirichlet distribution is also between 0 and 1. And that's actually what we need here for the class probabilities. Okay. And so far we've talked about the general ideas of mixture models. And for growth mixture models, it's just a type of mixture models. Okay. As we have already seen from part 1, growth curve models are important that can help us to investigate change over time. And growth mixture model is just an extension of growth curve models where we want to study different groups in the population and study their change, each group's change over time. So they are useful to track multiple latent classes or latent subgroups of individuals over time. Basically, growth curve model can be viewed as a special case of growth mixture models, where in growth curve model, there's just only one class, but growth mixture model is like more than one classes. And these classes may exhibit different qualities. For example, different classes may have different growth patterns, and different classes may, the growth, like different covariates may affect the growth differently for different classes. So when do we use growth mixture models? When we want to study the unobserved heterogeneity of growth trajectories, where we want to relax the single population assumptions, then we use growth mixture models. In that case, we classify individuals into distinct groups or categories based on individual response patterns. Okay. And it also allows for different classes of individuals to vary around different mean growth curves. And one thing that is very important is the class membership is unobserved, because if the class membership is known, then we can just use a multi-group analysis. Growth mixture models are also different from the conditional growth curve models. In part 1, when we talk about growth curve models, if we don't have any covariates in it, it's called unconditional growth curve models. But we also talk about the variance of growth curve models, where we can add time varying and time invariant covariates. And also the growth curve model can be used as building blocks for some bigger models, more complex models. So conditional growth curve models means that we have covariates added into the growth curve model to interpret the between person differences. Okay. So if we just think about conditional growth curve models, we have those covariates added that can be used to interpret why there are differences across different subjects. But it's different from growth mixture models, because growth curve models are more like a variable-centered analysis. It focuses on how different covariates can interpret the differences across subjects, but the growth mixture model is more like a person-centered analysis. We want to categorize or classify subjects into different latent classes. Okay, so this is example data from the early childhood longitudinal study programs, ECLS, and the data shown here is the reading scores. So from the trajectory plot, we see that all the subjects were measured at 4 time points, from the initial time point 0 to time point 3. Okay, and we have the reading scores recorded. And if we just fit a growth curve model, we'll see that we get the average growth at each time points, and it seems like there is an increase or slight increase from time 1 to time 4. Okay. Like I said earlier, the growth curve model, traditional growth curve model, really focus on the conditional mean of the data. So we're actually looking for the average trajectory or the overall trajectory, and all the deviance from the overall trajectories are viewed as the between person variabilities. And we can use different covariates to interpret those differences. Okay. But by closely looking at this data, we can see that it seems for the upper level, like these groups or those classes, they are growing faster. They have higher initial values, and it seems that they also have a faster change from time 1 to time 4. And for those people at the bottom who are with relative low reading scores, it seems like they are not changing much. So potentially there might be latent classes. And in fact, if we fit a mixture model to this, we can see that there might be 3 latent classes. For the green one here, this group have the lowest starting value, and the rate of change is close to 0. So the line is more like flat. And for the blue line here, it's also not changing from time 1 to time 4 much, but they have a higher initial value. But for the third group up here, these people actually have a much higher initial reading scores, and also the rate of change is higher. So their reading ability increased faster than all the other groups. And if we observe such a pattern by looking at the trajectory plots, then we definitely would think like we can fit a growth mixture model to the data. And a lot of times in practice, if you see a big variations in your population for a growth curve model, and the population also composite of many different subgroups, then you can also consider using the growth mixture models. Okay. The growth mixture model equations are very similar to the growth curve models. If you see the equation here, you probably see, oh, it seems like they are just the same as what we've seen in part 1 when I showed you the equations for growth curve models. The only difference is now for each of the model parameters, it also have a subscript G, which represent this parameter values for the G's group. Okay. In growth mixture models, each latent class can have different parameters, and that's just indicated by this G. For example, if G equals 1 or 2, group 1 or group 2, these values could be different. Okay. And for a linear growth curve model, each class may just have a different average intercept, average slope, intra-individual Merriam error variance, and the covariance matrix of latent intercept and slope. This covariance matrix include the variance of latent intercepts, the variance of the latent slope, and the covariance between intercept and slope. Okay, and in the traditional growth mixture models, we assume the Merriam errors follow a multivariate normal distribution at level 1, and also for the level 2, the random coefficients, they together follow a multivariate normal distribution as well, with a covariance matrix psi j. Okay. And in this model, from this equation, we see that we have many parameters to estimate. Basically, for each latent class or each subgroup or each subpopulation, we need to estimate the average intercept, the average slope, and the variance of intra-individual measurement errors, that's the level 1 residual variance. And also for the level 2 residual variance covariance matrix, we need to estimate the variance of latent intercept, variance of latent slope, and the covariance between intercept and slope. So within each latent class, there are 6 parameters to be estimated. If there are more than one, or actually for GMM, definitely more than one. So if there are 2 groups, then it's 12 parameters, 3 groups, and then it's 18 parameters. But remember, we also need to add the class proportions as another few parameters. Okay, so with the number of classes go up, the model complexity can increase quickly. And to reduce the model complexity, we can assume that the variance and the covariances are the same across latent classes or subpopulations. And in practice, that's very common see. So basically all the variances and covariances are assumed to be, or constrained to be, equal across different latent classes. So we only need to estimate one set of that. And for all the fixed effects, like the average slope, average intercept, those we assume to be different across different latent classes. Okay. Group membership is recorded like, where we can just call it as an indicator, Zij. It equals 1 if the subject I is in the J's group, and equals 0 if it's not in the J's group. But the group membership follow a multinomial distribution with a hyperparameters lambda, or with parameters lambda. Okay, and we can just specify priors for those model parameters, just as what we did for traditional growth curve models. And we don't really need to specify priors for the group membership, because it can be just sampled from the data augmentation approach, but we do need to specify a prior for the parameter lambda, which is the class proportions. And lambda follow a Dirichlet distribution. This is the same, just like I talked previously about just the mixture model, not even the gross mixture model yet. So lambda follow a Dirichlet distribution, which is multinomial, which is a multivariate generalization of a beta distribution. And with the priors and with the function, with the equations of growth mixture models, we can specify the likelihood. So with the priors and the likelihood, we can get the posterior distributions of the model parameters using Bayesian MCMC procedures. Okay. For growth mixture models, here I actually listed a rough analysis steps for that. What I want to emphasize here is, although I actually put them into 6 steps, or summarize roughly to 6 steps, but growth mixture models can be very complicated. And for each of the steps, there are many potential issues. So I'm going to go through these steps, and I'm going to add some discussions while I'm going through these steps. But for today's workshop, because of the time limit, it's just not possible to talk about everything. I'm only going to give a simplified version of it using the Bayesian method. We can compare, we can just fit some unconditional growth mixture models, excuse me, and then we can compare some of the growth mixture models based on Bayesian model selection criteria. Okay, so generally, when we consider using growth mixture model, step 1, we fit a 1-class model. So a 1-class model, basically just a growth curve model. Why do we need to do that? There are different purposes. One thing is that we want to see if it's necessary to really go further to fit a growth mixture model. So we fit a 1-class model and to see if there are truly population heterogeneity. if the variances or the variance of the latent intercept, latent slope, or the variance of the random coefficients are small, then it probably doesn't make sense to go further to fit growth mixture models. Okay, for another thing, when we fit a one class model, we basically look at our data, we plot our data, and also we try to figure out the parametric form of the growth trajectory. So whether it's linear or polynomial or some other nonlinear exponential or other types of growth curves. So for one class model, it really just gave us a good start to think about what the growth curve is really like and whether we want to go further to fit growth mixture models. And then step 2, we specify unconditional growth mixture models. Okay, so in these steps, we fit growth mixture models without covariates. On a side note, some researchers would suggest to fit conditional growth mixture models from the very beginning, like use the covariates that makes theoretically makes sense to add to the model, but also that will add the complexity of the growth mixture model. So I'm actually using this approach that is also supported many researchers. So specify unconditional growth mixture models are growth mixture model without covariates. We just look at the change pattern. In this case, we can fit a 1 class model, 2 class model, 3 class model, 4 class model, 5 class model. And depending on the sample size, you can fit many classes. But remember that when you have more classes, the number of parameters actually goes up quickly, and the model complexity also goes up quickly. And besides that, it not only include just those different number of classes. For each number of classes, for example, for a 2-class model, there are actually different variants. For example, we can just constrain that there's no variance for intercept and no variance for slope. That's a model, right? That's still a 2-class model. And also we can freely estimate the variance of intercept and not the variance of slope or vice versa, or we can also constrain all the variances for intercept and slope are the same across different across different latent classes. So there are a lot different variants for those, even just for a 2-class model. So although it's just a step 2, in practice, we may end up with a long list of models. So with those long list of models, then the third step would be determining the number of classes. Okay. And also like determine or try to find the best model. Okay. So to determine the number of classes, it's also a complicated issue because it depends on many factors. It's not only like, oh, I check the model fit and I find the best fit model. But in fact, even by checking the model fit, there are different model selection criteria, like different model fit statistics that you can use, and they sometimes give different conclusions. And in terms to determine the number of classes, we look at the model fit. That's an important criteria. But we also need to think about the interpretations, or whether those latent classes make sense in practice, and also whether some of the latent classes have too few subjects. For example, if the percentage of the subjects is below 5%, does that still make sense to have that additional latent class there? And after that, we go to step 4, we check the convergence of the model in the Bayesian framework, and we also check some other potential issues to make sure the model or the number of classes we select have no problem. Okay, and then for step 5, typically we can then add covariates and fit conditional models to see whether some of the covariates can interpret the between subject differences in the change, and also whether some of the covariates can even explain the class memberships. And sometimes researchers may even go further to step 6, sorry, where the consequences can be handled. So, for example, if we are looking at the cognitive abilities for young children, and we may want to know their academic achievement as adolescents. So for different classes, we want to know whether different classes may result in different academic achievement skills, okay? In that case, the consequences can be handled as statistical outcomes predicted by the latent classes or as sequential growth processes. But just like I said, these are like each of the steps include a lot of issues that we can take care of. So in today's workshop, I'm only going to give a very simplified Bayesian version of doing the growth mixture model. So we're going to fit a 1-class growth mixture model and 2-class growth mixture model. I tried 3, but it didn't converge for non-informative prior, so we'll talk more about that later. And then we do the model assessment. We compare those models and find which model has the best fit. So I'm not really touching any substantive theories, or I'm not making any decisions based on the real situations. But when it gets to that in practice, it could be more complicated. But also I want to emphasize that the substantive theory where the interpretations are very important in the growth mixture modeling framework. All right, so in the Bayesian framework, when we want to compare models, when we want to do model assessment, we can use different model assessment criteria. So in today's workshop, we're only going to talk about DIC and WAIC. There are other commonly used criteria such as posterior predicted p-value, PPP values, or like LOO, cross-validation. And those are also very commonly used, but in this workshop, because of the time limit, I will only talk about DIC and WAIC. And DIC, based on the name, deviance information criteria, we need to calculate deviance, and DIC is actually based on the deviance plus the model complexity. So it's really just have the same idea of AIC and BIC. So we evaluate the model based on the model fit and also the model complexity. We hope the model to fit the data well. At the same time, we don't want the model to be too complex. Okay, the deviance is defined using this equation. So d of theta and x, and it has a -2 times the log likelihood plus some constant. And there are 2 ways we can calculate the deviance. The first way is we just use the point estimate of the parameter. So we just plug in the point estimate of the parameters into the formula and get the d hat, because that's the estimated deviance. Okay, and the second, we can take the expectation over the parameter space, and then we get this d bar. Okay. And the difference between d hat and d bar is called PD. So PD equals d bar minus d hat. It is a measure of effective number of parameters. Actually, it's also the complexity of the model. So DIC, the deviance information criteria, just equals d bar plus PD. Okay, so d bar is the deviance and the PD is the model complexity. Since PD is d bar minus d hat, so DIC also equals 2 times d bar minus d hat. And just like other information criteria like AIC and BICs, smaller DIC means a better model fit. However, there are many variants of DIC, and you need to check each software package to make sure you know what DIC is calculated for different software. Like in JAX that we're going to use in the practice session, Plummer, who developed JAX, proposed a correct DIC, and that is defined in this equation. And Plummer's DIC actually needs at least 2 MCMC chains. So if you want to get DIC values in RJAX package, you have to specify 2 Markov chains with 2 set of starting values, and then the package can give you the DIC value. But again, like I said earlier, the DIC calculated based on RJAX package is based on the conditional likelihood. So when the models have latent variables, it's not recommended to use. So we're going to use WAIC for gross mixture models later. Okay, WAIC was proposed in 2010, and it's also called widely available information criteria. And it's similar to DIC, we have to compute the effective number of parameters, and then it's defined actually using this equation. And luckily in our package view, it actually can help us to calculate WAIC, and I'll show you a few just later today, like how we calculate WAIC in R using the LU package. As I mentioned earlier, both WAIC and DIC calculation involves log likelihood. Okay, and those log likelihood can be calculated in 2 ways, which is conditional likelihood and marginal likelihood. That is, and for models without latent variables, for example, if the model is just for a regression model, then the conditional likelihood and marginal likelihood are actually just the same thing. And the conditional likelihood and marginal likelihood are only different when models have latent variables and random effects. Okay. Popular Bayesian software such as Box, JAX, and Stan define models using conditional likelihood. Basically, we have this P of Y conditional on the model parameters and also the random effects U. Okay. So it's conditional on the random effects. But marginal likelihood does not rely on random effects and latent variables. So what we do is just to integrate those latent variables out. So we integrate this U out and we get this marginal likelihood. Okay. So it's definitely need some additional step to get the marginal likelihood. Here is that like Box, JAX, and Stan provides the conditional likelihood, and some other software like M+, it argues that they use the marginal likelihood, provide the marginal likelihood, but they only use it when this integration can be solved analytically. And for some complex models, these integrals cannot be solved analytically, so you have to numerically integrate the latent variables out. In that case, M+ just doesn't provide the result. Okay, and why do we want to talk about conditional or marginal likelihoods? Because some recent studies have found that marginal likelihood information criteria have smaller Monte Carlo errors and better model selection results than the conditional likelihood-based information criteria in models with latent variables. So based on my simulation studies, even for growth curve models with latent variables, sometimes the model information criteria based on conditional likelihood could still be very misleading. And especially for mixture model, growth mixture models, the conditional likelihood-based DIC or WAIC values will not give you the correct number of latent classes. So we focus on marginal likelihood in this workshop. And since JAX only provide conditional likelihood-based DIC, so in R, we need to specify marginal likelihood injects, and we can use the marginal likelihood for the loop package to compute the marginal likelihood based WAIC. It's actually not complicated at all. So in JAX, what we need to do is we just need to add this line in our model part using the log density.norm function. So for the traditional gross mixture model, remember that all the model assume to follow a normal distribution. So that actually makes things much easier. And for more complex models, like some of the robust models using t-distributions, or even the robust analysis I mentioned, like based on conditional medians, that could be definitely more complicated. But for the traditional gross mixture model based on the normal distribution with normal assumptions, then this line would be enough. Okay, so in the model part, we add this log likelihood using the log density dot norm function, where the observed outcome variables YT is put here. And then we just need to specify the mean of it, or marginal mean of it, and also the precision parameter of it. So here in JAX, everything is based on precision, but precision is actually just the inverse of the variance. So we just need to calculate the expectation YT conditional on the fixed effects, and also the variance of YT conditional on the variance parameters. Okay, and they can just be calculated based on the model. So for the expectation, it just of YT, it equals the average intercept plus average slope times time. Okay, and for the variances, it equals the level 1 residual variance plus this is a variance of intercept plus a variance of slope times the time square plus 2 times the covariance between intercept and slope times time. So with this information, we can actually just get the log likelihood. So I'm going to use the example with this one class model to start. Okay. For one class model, it's actually just the same as the growth curve model, right? So in part 1, we look at the code for JAX code for growth curve models. And we said, oh, here's the model part. This is how we specify the likelihood of the model. But when we want to get the WAIC, like I mentioned earlier, we need to get the marginal log likelihood. And in that way, we just need to add this line. So that is just this line we add to the model part. Okay, so everything else is the same for the I subject from 1 for the I subject from 1 to n, and for the time from time 1 to time t, and then the YT just follow normal distribution, and then this mean is a linear regression of time. But also now we have this log likelihood specified. In this log density norm function, we need to let it know the mean of Y and the precision of Y, or the variance of Y. So we calculate the mean of Y using this, which is a fixed effect intercept times the time times the slope, fixed slope, or average slope. And then, oh yeah, this part. So this is the fixed mu of LS, and mu of LS1 is average intercept and this average slope. And also we get the variance of it by following the equations in the previous slides. Okay. All right, so that's the model. Other than that, it's just stay the same. So the random intercept and slope and follow a multivariate normal distribution. Yeah. Okay, and how we specify priors and how we reorganize the parameters are the same as the growth curve models. But now we also need to have the log likelihood, like log-like as a parameter. So log like, we want to also monitor that when we do the MCMC iterations, okay? And then we compile our model by put the model data initial values together. And in this case, I'm setting the number of chance to be 2, just give you more options. Like previously in the growth curve models, I just use a 1. But if you set it as a 2, it just gives you more options for you to calculate DIC directly from JAX. And also for some convergence tasks like Gilman's task, it requires at least 2 chance in order to get the convergence task done, okay? So I just gave you more options. You'll see the code from our course website. Okay, and then we update our model and set after by assigning the burning period. So within the burning period, which is the first 5,000 iteration, we just throw them away because they didn't converge. And after that, we record the CODA samples and then use the CODA samples to calculate the, or to just, those are the posterior distribution, empirical posterior distributions. Okay. Notice that we have to save the log likelihood values, and finally in the LU package, library LU, and we can calculate WIC just using the WIC function. And for this one class model, the WIC value is 10,224.7. Okay, here I want to emphasize again that because this is just a 3-hour workshop, so I assume that you already know R and you already know some Bayesian and you already know some longitudinal data analysis. If not, that's also fine. So I gave you the materials and all the code. They should be readily run. So if you have other questions or if your code doesn't work, you can email me after this workshop. I'll be happy to answer any questions from you. And also in the future, we hope to have a longer version of this workshop. Actually, last year we had a 2-day workshop for Bayesian longitudinal data modeling. So at that time, it's not just me as the only instructor. We have another main instructor and 2 guest speakers. And actually, some materials from today on growth mixture models, I actually used some slides from Han Du, who is another instructor of last year's, and also used Sarah DePauli's some of the figures from her growth mixture model lecture. Okay. Okay, so regarding the model selection, we just did the step 1, which is fit a 1-class model, and then we can fit unconditional model with more than 1 classes, right? We can fit a 2-class model, 3-class model, and in the course website, we provide the code with no constraints, where we freely estimate all the model parameters for different latent classes, but that model just takes a long time to converge. So I'm not going to illustrate that in our lab session. We also fit a model with constraints where all the variances and covariances are assumed to be equal across different latent classes, and that model takes a shorter time to converge. And I can show you that when we get to the practice part. Okay, so let's first look at the 2-class model. How do we fit a 2-class growth mixture model? Okay, we start again from the smaller part in JAX, and for the I subject, now we have to specify the class membership or the group membership. It follows a multinomial distribution with parameters lambda. Since this is a 2-class model, so we only have 2 lambdas. Lambda 1 is for the probability for class 1, and lambda 2 is the probability for class 2. Okay, and then for these for each of the subject I, and then from time 1 to time t, we can model the growth curves. Okay, and in this model, like I said, we assume all the variances to be the same across different subjects, and all the covariances are also the same across different subjects. So in that case, the group membership, this member I, will only work for the fixed effects. Okay, so that's why you see that for this YIT, it still just follow a normal distribution with this mean and this is the precision parameter, because it's the same for different subjects, then that's just a one parameter. If we freely allow this to be different for different classes, then we have to add a bracket afterwards. It just show the membership of this parameter, but I have the code available on the course website, so you can directly use it. And then for this mu of y, which is a mean, it actually equals the latent intercept plus latent slope times the time, okay, t minus 1. And again, we have to calculate the expected value of y based on the fixed effects for the G's component. Remember, fixed effect has to be for the G's component. And also we calculate the variance of it, but then because the variances are all the same, so you can see that there's no such members in this line, okay? And then we put the log likelihood value in, just using the log density norm function. And then just for the random effects, and this is the random intercept and slope together, they follow a multivariate normal distribution with the mean and the with the interception slopes. But notice that this is the average intercept and slope for different classes are different. So we have this member, the group member indicators here. All right, and this is just the rest part of the model, like how we specify the variances, the priors for the variances, the priors for the intercept and slopes for different classes. One thing you have noticed here is just for the intercept of these, this is the truncated normal. This is just to make sure the intercept of the first group is bigger than the intercept for the second group. Okay, so why do we need to set this? Because we want to make sure that those labels are not switching, because the ordering of the classes are not defined in growth mixture model. So we can actually add this constraint to make sure the label, the class 1 always stay as class 1, and class 2 is always stay like class 2. So the labels are not switching. Okay. All right, this is for the identification purpose. And also here is the priors for the covariance matrix and the priors for lambda, which is the class probabilities follow a Dirichlet distribution. And then we can organize all the parameters, like we can have the intercept for class 1, slope for class 1, intercept for class 2, slope for class 2, and all the covariances and variance. These are the same for different classes, so it's just one thing. And also for lambda, which is the probability for class 1 and probability for class 2. Okay, so once we have that, we can just specify initial values. Yeah, I just give you some additional information. Like these are all available on all available on the course website. So yeah. And then after we have the log likelihood saved, we can just use the loop package to calculate the WAIC values. Okay, and then the WAIC for the 2-class model is 9,783, which is smaller than the 1-class model, where the WAIC is 10,000 something. Okay. We also try can try the model with 3 clusters, you can actually generalize the code from a 2-class model to a 3-class model. But with the non-informative priors, like we said in the model, the 3-class model just didn't converge. Actually, the data are simulated data, and we know what the true model is. The true model is just a 2-class model because we simulated data from 2 latent classes. That also makes sense for 3-class model didn't converge. But in practice, if you think a more complex model makes sense, then we can use informative priors in order to work on the convergence of the model. Okay, and comparing the model with 1 class and with 2 classes, the model with 2 classes have a better model fit. Just like I said, this is really a very simplified version of growth mixture modeling. The real problems can be much more complicated than that. So the potential issues that we need to consider include class separation, class enumeration, and all these on the list. Basic class separation is a concept that helps to define how distinct or not the latent groups are from one another. So whether the subpopulations different substantively from each other. Typically, separations will be defined in terms of how disparate parameters values are, and as well as substantive interpretations. Class enumeration is to determine the number of latent classes, like how many classes are there. It's an issue that is closely tied to the idea of a class separation, because if the class separation is big, then it's easier to distinguish them and the class enumeration would be more accurate. But if the class separation is small, they're mixed together, then the class enumeration would be not as accurate. And the class enumeration is also related to other things like the balance of the groups. Like if some groups have much larger sample size, the other groups have much fewer, then it also would affect the accuracy of the class enumeration. Basically, we just care about how many latent classes are there and how many are there. But some researchers may just argue that the existence of multiple classes may be due to non-normally distributed data. For example, if we fit a mixture model to a data with skewed distributions, then the researcher may want to say, is that truly some latent classes exist, or what about just fit a robust analysis with the skewed outcome variables? Okay. So, but generally the class enumeration could be a complicated issue, and also it is determined by not just the model fit, but also the interpretations of your model. Okay. And even just for the model fit, we have to figure out which model selection criteria to use. Not in the Bayesian framework, even for the frequentist framework, there are many criteria to use to decide which model fits the data the best. And then in Bayesian, we know there are also many different criteria like DIC, AIC that we've covered today. And there are also LLO, the PPP values. So which model selection criteria to use, because they may just give us slightly different results and sometimes quite different results. For example, one criterion may prefer a 2-class model, the other prefers a 3-class model. Which one do you want to use? In that case, it may depend on the interpretation of the model. And also we need to look at very closely at the posteriors and see whether a 2-class model or a 3-class model makes sense. Okay, and also we said even for the WAIC or DIC we want that to be based on marginal likelihood, right? Not conditional likelihood. Okay. And when all these issues of class separation, class enumeration, and the model selection criteria are combined with small samples, then the estimation can become even more complex. And the small samples are not just for the overall sample size. The relative class size also matters. Like I said about the balance of your groups, right? If we have balanced groups, like all the groups have about the same number of subjects, then that probably give us the best class enumeration. But when one class is very large, although one class is very large, but the second class is very small, then we still have problems in estimating the model. And the problems may include non-convergence. So we already seen that for our, even the simulated data for a 3-class model, it didn't converge. And in practice, the convergence issue will be something people care most. And when the model didn't converge, we can try to use informative priors, and informative priors in the Bayesian framework showed very promising in terms of solving the convergence issue. And based on one of my previous simulation study, I was actually surprised that if non-informative priors were used for very simple gross mixture models, the convergence rate could be very low, as like lower than 15%. But when the informative priors were used, the convergence rate can be improved dramatically. Another problem I just already mentioned briefly a few minutes ago is a label switching problem. It occurs when the ordering of the latent class is arbitrarily changed during the MCMC procedure. And it is very common since the ordering of the classes are typically not defined within the mixture model. So what we can do is, like based on our previous example, what I did is I just add something here. So to make sure the intercept for the first class is smaller than the intercept for the second class. So it's truncated the values from -infinity to the mean of the intercept of the second class. Okay. Regarding the label switching problem, there are 2 types that can occur. The first type is within chain label switching. Basically, such a single chain switches back and forth between different latent classes. A sign of that would be like if you plot the history plots for the Markov chains, you'll see that for the model parameters, the value actually jump back and forth. And for the class proportion, it's even more obvious, like for class 1 proportion is suddenly, it was close to 0 and suddenly close to 1, and basically just switched for class 1 and class 2 proportion. That means it's the label switched, okay? Oh, this slide was where these 2 figures were copied from Depoli's last year's slide. Okay, and besides that, we also have a between chain label switching. So when multiple chains are used, then the values across chains can really jump from one chain to the other. Regarding those label switching issues, the solutions could be not that hard. So we can just work with a single chain rather than multiple chains to prevent the issue of between chain label switching. And for the within chain label switching issue, it can be really largely or effectively prevented by using the identifiable constraints on the disparate parameters across classes. This is really like what I just showed you in the code where we were constraining one parameter in one class to be smaller than the other class or bigger than the values of the parameters in the other class. So by just setting that, the classes will not switch. So the label switching issue can be resolved. Okay, and even after that, we have to really carefully inspect the chains and the resulting posteriors for any signs of label switching. Sometimes those signs include empty classes. Okay, some take-home messages here. Gross mixture models or gross mixture analysis is a tool useful to explore latent heterogeneity in chain trajectories. Based on the literature, frequentist method may not perform well, especially for poor class separation and small sample sizes, small class sizes. And Bayesian method may provide may help elevate the problem. Will give just a useful or helpful, powerful alternative to the frequentist method by using some informative priors. Okay, Bayesian model selection should be based on marginal likelihood. Okay. Also, although the Bayesian gross mixture model is powerful and flexible, we have to really be mindful of potential issues, including class separation, class numeration, and also small sample sizes, prior issues, and label switching problems. Like I said, gross mixture modeling is really complicated study, okay? And the last thing is substitute theory is important in gross mixture modeling. Although in today's workshop, I didn't really talk much about the substitute theory, but it's definitely very important in gross mixture model because that actually makes the interpretation make sense. And like I said, in step 2 of the gross mixture model, I give the rough summaries. We may end up to have a long list of models, and the substitutive theory will guide us towards the model that are most useful to us. Okay. Right. Okay, so that's for this part, and we're going to do the practice in a minute.